review. So what I'm going to do with this review is different from other reviews. Instead of actually writing through the problem, because I want to go over each exam and I don't want to like solve each problem. We're going to be here for like 3 hours if we do that, hopefully. So this is what we're going to do. So I solved the problems myself and we'll just go over the solutions. If anyone has questions, just say something, all right? Okay, so for the first problem. So the first problem is on exam 3. Let me just pull up on my phone. Exam 1, sorry. Exam solutions. And so exam 1, problem 1 is asking consider a particle moving in 1 dimensions with position x equals x and the linear momentum operator. Show the commentators Tx, give the commentator momentum times x commutes. All right. So they basically want you to show that that this is equal to this here, and they want you to find what C is. And to do that, what you're basically gonna do is basically commutator rules, which product rule and everything. So to find the commutator of this, you would have to apply the operator that's beginning, so this one, and then reverse the operator here. And then you apply it to the arbitrary function f. Now, when you do that, the result you're gonna have is you're gonna have a taking a derivative first, taking the derivative of f, and then afterwards you have to do a product rule with that new with f prime and x times negative ih bar, and minus x, and then you're gonna do the opposite, which would be this here, and you're gonna apply the second 2 derivatives on here onto f. Now, when you do that, you're gonna show up with this expression here, and you're gonna just cross out the second derivative times x, and then you'll have this here. And the trick to this problem is you solve what the commutator is, but you have to find, you have to also find what C is equal to. I mean, the main problem, the main goal of this problem. So to do that, you go to the next page. So basically you equal the commutator, this commutator, to basically C of P of X, and you, which is the momentum. You expand out the momentum operator, and then you get, you cross out terms, so you're left with C on the left side. So you basically divide by this onto here, and the square just gets gets taken away, and then the derivative just cancels out, and so you're gonna have this as your answer. And I'll just erase this. Oh. Now, does anybody want me to go through the problem again, or have any questions about it? Any questions at all? Okay.
No.
Oh, you have a question?
No, I said I'm good. Thank you.
You're good? Okay. All right. So let's go to the next problem. So the next problem is asking you to consider a particle moving a mass m in a 2-dimensional box with the length of L of x equal to 2 angstroms and L of y equal to 4 angstroms, where 1 angstrom is equal to 10 to the negative 9 meters. So using the notation E, Nx, Ny for the energy eigenvalue corresponding to the quantum number Nx, find the value of the energy ratio E of 2,2 over E of 1,1. So basically what you have to do is just plug in chug pretty much. So you get the equation here. Oh wait, you get the equation here. And then you divide E of 2,2 over E of 1,1, which is what they want you to find. You cross out the constant in front because they're not affected. M is still the same. And then you plug in what L of x and Ly is. and then you just basically just solve it, and then you get your answer to be 4. That's straightforward. The next problem is I put you didn't need to know bracket notation to do this problem, but I just considered it a lot easier when you like if you are doing the final that actually the same exact problem, bracket notation is like a lot easier to do. So pretty much what you have to do is find the expectation value for y, and to find the expectation value for y, you apply this here. Y only affects the y part of the wave function. So you're going to have two terms, which are going to be the wave function in terms of y and the wave function in terms of x. The wave function in terms of x is already normalized, and y doesn't affect it at all. So we can just cross it out. That's normalized, and that's equal to 1. And for this here, since we know that the expectation value of x is Lx over 2, is the same thing for y, which is Ly over 2. So you don't need to solve the whole integral. You just need to equal it to Ly over 2. And you're given what Ly is, which is, I believe, 4 angstroms. So it's just 4 divided by 2, and which is equal to 2 angstroms. Now, does anyone have any questions about this? Straightforward? Good? Okay. Okay, so in problem 3, it's asking you to find the eigenvalue of it's asking you to find the eigenvalue of this function here, and we see if it's an eigenfunction of that operator. So we apply the operator on here, and we see if the function tolerates the operator, which means you'll have the same function. So after applying this, you're gonna do a chain rule because it's an exponential, and then you're gonna have 3i be out of the exponential, and then from there we see that the function's maintained. There's no like any of these right multiplied by each other or anything like that. So that means that this is satisfied, which means this is equal to this, and this is its eigenvalue. Would be if you're taking the derivative 3 times. So because you're dealing with an exponential and you're taking the derivative 3 times, you don't need to take the derivative and derivative again. You just have to take the derivative to the third. So basically, it's the chain rule 3 times, which is just this 3 times. And so what you're going to find is this is going to be equal to this eigenvalue here. All right. And next part would be this. They want to show if this commutes. This is just 2 derivative operators. You really think about it. If we take out the constants and we take the derivative of this and the derivative times the derivative to the third power is the derivative to the fourth power. So we have like a derivative to the, f to the fourth power. The fourth derivative of f here, and that's subtracted to it equal to 0. And so when you're given a question like this, and it's asking you to find a commutator of 2 derivatives, like the n power, it's good to know this. If they're multiplied by like different constants, and the only difference is that they're raised to a different derivative. So let's say if this is the first derivative and the second derivative, then they'll always commute. So if you're given a question like that, you should always assume that this is going to equal to 0. And so just keep in mind when you're solving these commutator problems. Now, does anyone have any questions about this? Any at all? Okay, so we'll just get to the next part. And this problem 4 is normalization problem. So this one you have to actually use intervals. So basically you have to just multiply a wave function by itself. Because there's no I parts, it's just literally the wave function squared. You're gonna have n squared out here. Normalization condition, it has to equal to 1 for all space, meaning 100% probability of finding that electron when you look through all space. And then when you solve this, you're gonna get that this is, okay, you expand this out, and then when you take the integral of this, you're gonna have this expression. And then once you do that, you plug in 1 and -1, and you subtract them by each other. And what you're gonna get is the answer gonna be radical 5 over 8. And you multiply this normalization constant to the original wave function to have it normalized. Now, Does anyone want me to walk through the math or anything? Is everybody good with this question? Okay, so I'll go on to the next part. So let's say we have problem 5 has to do with let's give me a second. Let me just airdrop this to my good notes so it's easier to follow along. Okay, so consider a particle moving in mass m from x equals negative x in the positive direction with energy E, with a potential energy V of x, and for x is less than, it's x is less than 0, region 1. And for V of x is equal to V of 0 for x is greater than or equal to 0, region 2. And you can see the figure below. And the wave function has the form here. Okay. All right, so let me go back to my notes. So to give us each of the wave function in each region. So in the first question is asking you to, find the value of the linear momentum for the particle 1 in region 1, moving in the positive direction. Now, when it's talking about the positive direction, it's talking about where the exponent is positive, because when you use the momentum operator on this, you're gonna have it gonna be positive. So I could apply the momentum operator if I wanted to and get this value k of 1, but I'm not gonna do that because it's a lot easier just to look at the exponent when it's talking about a particle moving in 1 dimensions. Then just look at the exponent. If the exponent k of 1 is the value, and they give you k of 1 is equal to this. So when you take the radical of this, you're gonna get this answer. So if you're talking about a particle moving in one dimensions, then look at that wave function. If it's positive, then it's it's going to the right, and if it's negative, then it's going to the left. All right, and if you apply the linear momentum operator, you get the same result. I'm just skipping ahead to that because it's like a lot easier to look at the exponent without the x and I. Okay, so then it's asking you to find a potential depth. Now this one I know is the most difficult one, difficult question. So you just split up the integrals to make it makes a lot of sense. So first off, let's do this integral first. First, it's asking you potential depth in region 2. So you look at region 2 here, and then you take the integral from 0 to infinity, because those are the boundary conditions for that region. So 0 to infinity, because x is less than or greater to, x is greater than or less than 0, and this is x is less than 0. So its boundary conditions for this would be 0 to infinity. And so when you take the integral of that, you're gonna get this term, because it's the opposite of the chain rule, so it's divided by that exponent. So when you do 0 to infinity, because if you apply affinity to negative, so negative infinity will always go towards 0. So that means that this term will equal to 0. And then you do 0, so it's going to be negative 1 over negative 2k. So 0 minus negative 1 over 2k times that d squared, which we put as a constant on the side of the interval. We're going to get d squared over 2k. And skip ahead to this. And for the second part of the integral, we're going to have d squared d squared times that x. So he given us a something for that. So if you look right here, he said that we can use this here to solve for an integral. So then basically applying whatever's on the exponent, it's going to be divided by this and a squared below. So by applying that and plugging in, we get that this is equal to this. And so just like how we did before, it might be weird because we have an infinity we're plugging in, oh wait, let me just put an X here. But we can plug in affinity to the X, or we can plug it into the X and the exponent. Exponents grow faster than polynomials or linear functions. So when it's asking you an exponential times a polynomial or anything like that, and when it's asking you to multiply by infinity, then we're gonna always go for the exponential value. So in this case, it's going in negative infinity, so that means it's going to be equal to 0. And then when we put it to 0, we're just going to be left off with this term, and then we're going to have this term below. And then what we're going to have here is the result here. And then we divide each of the answers that we got, and then we're going to get this answer. Which we proved in lecture that this was related to the potential depth. So the greater the energy, the greater V0 is, that means there's going to be less likely that you're going to penetrate that barrier. Okay, so what's the next part? All right, so does anyone have any questions about this at all? None at all? Okay, so let me put on to notes for the next part. Okay, so problem 1 is asking you to find it has a multi-electron system with 4 electrons, and its nucleus includes 4 protons. So assuming that the mass of the nucleus is infinite compared to with the mass of the electron, write the expression Hamiltonian operator for the beryllium atom in atomic units. So first off, what we're gonna do is, Veneri did his differently. He just wrote it out separately, but what I did was I wrote down each of the terms separately. So for multi-electron systems, we have the kinetic energy of the electron, the attraction of the electron to the nucleus, and the electron-electron repulsion. And for multi-electrons, I split off these terms. So when you solve this problem, I would suggest that you write out the full Hamiltonian, and then you split off the Hamiltonian, equal it to find out what each value is. So for the first part, we have the kinetic energy of the electrons. Since there's 4 electrons, we're going to have 4 terms, each to the squared. I forgot to put a squared here. And that's kinetic energy of each electron. And this is shown by this equation here. And this is I. And then we're going to have the attraction to the nucleus. Each of the electrons are going to be attracted to the nucleus, and it's going to be multiplied by the charge of the nucleus too. So right here, so we plug in the charge in the nucleus. Since it's beryllium has 4 protons, it's going to be charge of 4, and so it's going to be 4 that's for electron 1, is 4 over electron 2, and for electron 3, and 4 over electron 4. So then the next part is the tricky part, is the hardest part of this. It's electron-electron repulsion. Now, what you do for this is you put each combination, so you count the interactions, but you don't count the interaction twice. So you say what electron 1 does on electron 2, electron 2 does on electron 3, 2 to 4, 1 to 4, 1 to 3, and 3 to 4. And you do all that until you run out of combinations. So basically, for this question, you just have to, I would say if he asks you like 4 electrons, you're gonna always have like 6 terms. All right, so I also drew a picture here showing how each electron exerts 1 force onto each other. You can do this on a test too, just to verify if you got this correct. I would do the combination, and if you feel like you missed something, then I'd say draw that, see what electron does on each electron, and after you're done drawing arrows, you pretty much have your full Hamiltonian for electron-electron repulsion. Okay, so for the next part, it's asking you to do the same thing, but this time it's beryllium beryllium plus, which means it has 3 electrons because it doesn't have an electron. So basically, it has 1 less electron, I mean. So it's kinetic energy of 3 electrons. So it's basically the same thing, but without the, I keep forgetting to put the square here, but it's without the 4th term. And the same thing here, but it's without the 4th term. And then here, for electron-electron repulsion, we just have different combinations, and we're gonna have 3 terms here. So for 3 electrons, you're gonna have 3 interactions. Now, does anyone have any questions about that? Okay, so the same thing here. It's a lot easier because we have 2 electrons, and we pretty much do the same thing, and the last term is 1, 2, and we can't have a 2, 1 because electron 1 can only interact with themselves once. And the part D is the tricky part. So it's asking you to write down the 0 order Hamiltonian. So that's the reference. So the reference is a reference we know, and a multi-electron is like a reference we really don't know much about. So we're gonna include every Hamiltonian aside from the electron, the multi-electron system, because that's what's different about the system. So basically we list all the Hamiltonians that are included in our reference like a 1 electron system. So it's kinetic energy of each electron and the potential energy to an attraction to the nucleus. So from that, you would get that this is here, and we know that we learned in lecture that we solved it to be 2 Hamiltonians from 1 and 2, and this would just be twice because we have 2 electrons and we're not counting electron-electron repulsion. This would be twice the energy of that 2 times the energy of E1 of beryllium 3 plus. So then plugging it in, we find that this is negative 16 Hartrees. All right, does anyone have any questions about that? Okay, so next part is okay. So consider an atomic wave function describing a excited state of lithium in which the electrons are in a 1s atomic orbital and others are in a 3s atomic orbital. So as indicate the symmetry of each wave function with respect to the interchange of space of the 2 electrons based on these results. Indicate which function is satisfactory approximates to the 1s1 and 3s1 excited states of lithium plus. So basically what you need to do is find the right wave function for this system. Now, I put a little notes before. So electrons are fermions, which means that if you were to interchange them in space, that would mean that they would have to have like a negative wave function, which is shown here. So if we were to apply this operator, which is called, this operator exchanges symmetry. So it turns 1 to 2 and 2 to 1. And so what we're trying to do is to figure out this question, we need to apply this operator to each of the wave functions to see if we can get to this answer. So on part A, so what we do is apply the operator 1, 2 onto the first wave function A. And then from doing that, we get this answer. Now this answer can't be, is not equal to the positive or negative of the original wave function, which means it's neither. And this is because we can't like put this in front and sorry, this is just not equal to the negative of the wave function. They're just different from each other. And we showed in next part here, this is so if we were to use this operator and exchange in space and turn 1 to 2 and 2 to 1, we would get that this is going to be equal to the negative of the original wave function, which means it's a good wave function to use. And this is shown here. If we were to rearrange this and put 1s1 1s2 in front and make that a negative, plus that 1s2, 3s1 positive, and this will just be the negative of that original wave function that we have, which is here. Okay, so the third one, we apply the operator, and then I didn't write out the wave function, but I just wrote out the result of applying that operator. And this would be the same as the original. So the spatial part's the same, but the spin part is different. And this would be so the spin part would be negative, and this would coincide with a negative thus of the original wave function. Now, the next part is to find a normalization constant of each of the right wave function. So we have to find a normalization constant for this one and for this one. So for a simple trick is to basically for wave function in this form, so like wave functions like this and or this. And when I say wave functions, I mean the spatial wave function and the spin wave function. So basically, if we have a wave function of this form, the normalization constant is equal to the number of electrons times the factorial. So in this case, I don't think he's going to ask you for like 3 electrons. If he's asking you for like a system of 2 electrons, then the normalization constant will be this. And for a wave function like this, so basically this here, then or this here, normalization constant will be equal to 1. And it's just shown equals to 1. So knowing that, we can plug in a normalization constant for the spatial part, which is equal to this, and for the spin part is equal to 1 times the original wave function, and now it'll be a normalization constant. For the next part, you have a wave function of this form, and so our normalization constant is equal to 1 over radical 2, and it's multiplied by 1 over radical 2 because it's another wave function of this form. Okay, so that's our question. Anyone have any questions? Any at all? Okay, so that's the next part. We have that we have to find a commutator of the, I think, rotational angular momentum and x. So to do that, what I did is I expanded it out, and we did the commutators by multiplying by x. So this is the result. So basically x multiplied by that this on the outside, we have x, right, that shows up here, and then x will be in front. Now the trick to this question is to for momentum. So basically the momentum here is momentum operator includes p of y is equal to negative h bar times the derivative in terms of y. But since we have x here acting on the momentum operator of y operating on x is in terms of a constant. So because x is a constant, we can put this, in the constant in terms of the derivative on the momentum operator in the y direction, we can put this in front of this, and we can cross out this term and this term. And after we cross out this term, all we're left with is this here. And we can't move this here because this is in terms of x, and this is momentum operating in x direction. So the derivative will not allow the x to be moved on the outside. So, and because of that, we have to keep it like this. But the y part we can put in front. We can pull out the y part, because if we pull out the y part, we can get this answer. And this here is just a commutator that we know, which is shown right here. And this commutator is is, oh wait, this is X. So this is, oh wait, no, it's not X. This commutator is equal to negative I H bar. I'll just put that here. And from that, we get our answer. And the trick to this question is to put it in a commutator that we already know, and then just give the answer to, and expand that commutator to the answer to the commutator we, the value of the commutator we know. Does anyone have any questions about this? Okay. If you guys have any questions, just don't be afraid to ask. Because, or if I'm moving too fast or anything, just let me know. Okay. So the next part of the question, the next question is to solve these intervals. And basically, you guys figure this is I believe this is the easiest part. I think definitely we will find something like this on your finals. So basically you apply this operator here, and you so SZ, which should be related to M. In this case, M is equal to 0. And so, wait, is this actually, this is the spin part, and this is beta. So this is this beta relates to a eigenvalue of negative 1 H bar. So then we have negative H bar, which is the eigenvalue for beta. But since there's two different spin parts, this would be, or these two spin parts will be orthogonal, which means this will equal to 0. And same, and this is basically almost same thing. When you apply this is for the spin up part. So that means when you apply it, you have H bar over 2. And because it's a spin up, which means it will be positive. And this, since this is but these two are orthogonal because you have a p orbital and we have an s orbital, which both have different eigenvalues, making them orthogonal, which will be equal to 0. So then you have L squared, and from this we know L is equal to 1 because it's a p orbital. And then we have L plus 1, and we plug in 1 down here, and then we see this is because these are both the same wave function and normalized, this is equal to 1. So then you're just left off with this, and then after that you plug in 1 and you get this answer 2 H bar. And right here you're gonna find that it's gonna be equal to E of n, or E3. And if you, why did I solve this? So this is like, oh, so this is equal to 0. I don't know why it's equal to 0, because they both have different quantum numbers, and you have different angular momentums. I'm thinking that, yeah. Okay. So, and then the last part is asking you to solve for this again. So you're gonna have E2, and these are both normalized wave functions. So this is gonna be equal to E2 times 1. So you can, for questions like this, you can just leave it as E2 because you're gonna know what you're talking about. Just don't work smarter, not harder. Don't like solve what E2 is equal to in hard trees. Just leave it as E2. Okay, does anyone have any questions on this at all?
No.
No? Okay. Okay, so next part is asking, let me ask you to pull up the question. Last part. Okay, so a rigid order with momentum I is known to be a state with eigenfunction y2 negative 1. What is the rotational energy in terms of I and H bar? So from this, we show irrotational can be found using this equation. You just plug in what L is equal to, which would be the first column number shown on here, which would be equal to 2. So then we plug in 2, and then we have 2 and 2 plus 1, and then we have 3 H bar. And so we plug in 2, and then we've got 3 H bar over I. Since we don't know what molecule this is, we don't have to know what I is. So we can just leave it as I. All right, and then it's asking for the length of magnitude L. So it's basically, you have to take the radical of L squared because this is literally L. So this is radical of L times L plus 1. And then you plug in what 2 and 2 again, and then you're going to get 6H bar. 6H bar. Yeah. 6H bar. Yeah. All right. Give me 1 second, guys. Let me just make sure I got something right. This will be H bar squared. H bar squared for the first part, and then it's going to be radical 6 times H bar. And so make sure I didn't do anything wrong for this. This is H bar squared and H bar squared. All right. Okay. So I correct those. And for the next part, it's asking you to X for LZ. So since they're giving you M is equal to -1, this is the second quantum number on that wave function. It's just going to be negative H bar. Okay. The last part of the question, I think, is the most difficult. It's pretty much to find an expectation value between the addition of the angular momentums in the opposite directions of Z. So the way to solve this is basically to find, we know that to find the magnitude of the angular momentum, you can use this equation by putting JZ on the other side. We get that this is going to be equal to this, which is equal to what this expectation value you're trying to find. And these are operators we know. So we can put this on the inside of our integral. And after putting the inside, we can split up our integrals and we can solve for this. And after solving for this, we plug in what L is equal to, what M is equal to, and you're going to get this, okay, 5H bar squared. Now, does anyone have any questions about this at all, especially part D? Okay, so go with next one. Okay, problem 1. I'm just pulling this up. Okay, so problem was asking you to is asking, okay, a helium atom has 2 electrons. It's asking me to write the Hamiltonian for helium H molecule and atomic units. Consider the intermolecular separation in R for each term in your answer. Indicate where the energy configuration is positive or negative and give your reasoning. Okay, so for this question, what they want you to do is find the total Hamiltonian, the electron Hamiltonian for a molecule. And so for electron Hamiltonian, when we don't have is the kinetic energy of the nuclei. So the kinetic energy of the nuclei will be left out, and because an electron Hamiltonian makes the nucleus freeze in space relative to electrons, because electrons are moving really fast, and so we can use this equation with these parts. And so we're going to use these parts aside from the, these parts aside from the kinetic energy of the nuclei. So basically what we need to do is what we do for a multi-electron. We expand out the Hamiltonian, and then we solve each part individually. So first is the kinetic energy of the electrons, which would be, since it's helium H, they have 3 electrons together with each shared between each other. So you're going to have 3 terms. And the next part is the attraction to the nucleus. Since we have 2 nuclei, we have each electron can be attracted to either nuclei. So we're going to have 6 terms. three terms are going to relate to the charge of the first nuclei. In this case, it will be helium, which has a charge of 1, and the second nuclei, which has a charge of 2 because it's helium. And then we include, this is a distance to hydrogen for electron 1, is just hydrogen electron 2, and the same thing for here for distance to helium from electron 1, 2, 3. Okay, and we just use the equations here to figure those out. And then finally, we have the electron repulsion. Since we have 3 electrons, we're gonna have 3 interactions, and show this here. And we should do each combination, and we show that each combination will only lead to these 3 terms. And finally, we have the electron repulsion. I mean, the nuclei repulsion. And so these nuclei can repel each other because they're both positively charged. So then we're going to have the charge of the first nuclei and the charge of the second nuclei multiplied by each other over the distance between each other, which it showed in the question that that's equal to the distance between each of the nuclei is r. So it's going to be 2 over r. Okay, next part would be doing the same thing, but with 2 electrons. So then we have the kinetic energy of the electron would be 2 electrons. So we have 2 terms attracted to each nuclei, which would be, I don't know why I included this, but I'll erase that. It will be 4 terms altogether because there's 2 electrons and there's 2 nuclei. And finally, we have electron repulsion, which will only have 1 interaction. And this is still the same thing because the number of nuclei did not change for the nuclei repulsion. And then the next part is asking you for the kinetic energy of the nuclei. So that would be just the same thing as the kinetic energy of electrons, but in this case, kinetic energy of the nuclei, so it's going to be H and He pretty much, and that's pretty much it. And so I think I skipped problem 2 because problem 2 is pretty much the same thing as problem 3. So yeah, it's basically the same thing as the last one in the last exam. So I skipped that one. But if you guys want me to do it, just let me know. But for problem 3, what we need to do is to find we have a first wave function here. And these two parts of the wave function are 2 different wave functions that are centered on an atom, and they're both normalized. And they have an overlap integral of this, and this is going to be equal to 0.193. And I want you to determine the ratio of C2 over C1 that makes these coefficients orthogonal to this. So to find this, we're trying to make or basically the overall goal is to make this orthogonal to this. So we use Brown-Niket notations and equal to 0. And then using the Brown-Niket notations, we have the first wave function, and then this is the second wave function. But we use, since this is in the Brown notation, the wave functions are going to be bras, and this is in the ket notations, the wave functions are going to be kets. And then what we do is we multiply this together, and then we get 0.893, and then we multiply this by this, and this is what you're going to get after you expand it out. Now, because of the question told us what each of the values is for, basically, they told us what, oh wait, too far. Too far. Okay. The question is pretty told us what each of the values are. Since this is normalized, then this is going to be equal to 1 and tells the overlap integral. the overlap integrals are equal to this. So then this is going to be equal to 1, which is shown here. And this is going to be equal to all right. Okay, you guys still hear me? Hello?
Yes.
Okay, thanks. All right, so then this is going to be equal to 1, and this is going to be equal to 1. And they give us a value of overlap integrals. So then we just plug in what the overlap integral is, and this is going to be integrals times 1. And so basically, what we do is we solve for C of 1 over C of 2. I mean, C of 2 over C of 1. So then we just plug everything in, and then we basically just solve for this. And I didn't bother to write the answer for this, but this is, if you plug this in, you'll just get a solution. I think you'll get around, did he even expand it out? Yeah, you'll get this answer. Yeah, so does anyone have any questions about problem 3? Okay, so next part. It's asking you for problem 4. The pi electron structure of molecule methylene glycopentane, which is this molecule here, has been studied in Hubble theory and is found to be a pi molecular orbital and increasing energy has the following expressions. Calculate the pi electron energy in carbon 1 of methylene glycopentane in the ground electron state. Okay, so for this question, I would, if you guys are good at Orgo, you probably know how to draw this. I would suggest that also, if they don't give you a figure, then try to ask the professor, oh, can you draw this or something? It's 50-50, they'll probably draw it for you. But if worst case scenario, it's a glycoprotein. So you're gonna have it have a double bond somewhere, like around here and right here. So it's asking you to calculate the pi electron energy in carbon 1 in the ground electron state. So basically, what you have to do is you plug in and you use the coefficients of, so basically it relates to the coefficient of electron 1 and basically all the coefficients that each are occupied. I should also start with that you have 4 electrons in conjugation of each other. So then you have, because it's 1, 2, 3, 4. So then you fill in each atomic orbital, and it has 2 electrons per orbital. So it's 1, 2, and then you're gonna have 2 of these contribute. So I should take a screenshot of this. This will help. Okay. So in this case, they're asking you for electron 1. So the pi charge on electron 1, which would be relates to this here and this here. And it only goes, and it's so according to this equation, it's the sum over occupied. So it'll be up to these 2 orbitals. So then we use the coefficients of these 2 and plug it in. So then it's multiplied by the number of electrons in that orbital. So for this, for the first one, we have the number of electrons to be 2 electrons, and this is multiplied by the coefficient squared. So then we have our first coefficient in this orbital to be this 0.06116 to the square, and then that's going to be plus two electrons in the second orbital times the coefficient second orbital to be 0.2535 squared, and this will be equal to, after summing these over, you'll get this answer. Okay, so the next question is the same. They want you to find the bond order and let's get the bond order. They want you to find the bond order between electron 1 and electron 4. It's pretty much the same thing as pi. Oh, the pi order. Pi charge. You just use the coefficient of the electron 1, electron 4. And so this goes to occupied, so it's pretty much the same process as part A. So then we get the product of the coefficient of the first electron and the coefficient of the fourth electron. So then we got this here, and then we got 4, and we have this, and it times the number of electrons, which would be 2, as we saw before. And then we have the second part would be the second orbital, which would be 2, because there's 2 electrons in the second orbital, times this coefficient and this coefficient. And part C is asking between 1 and 3, which is pretty much the same process, except we have this one we're plugging in place of electron 4, and this one for electron 4. And you should get this answer. Okay, so next part is asking you to do the same thing, but except for an excited state. I remember this question, so I don't have to go back. Let's see for the pi charge. So because we have 1 electron into the third orbital, that means the third orbital contributes, which would mean it'll be the sum. So if we go back to original, we have 2 electrons on the pi charge of 1, I think. Yeah, pi charge of 1. So then we have the same thing, 2 times the coefficient squared, and plus 1, because of the excited state, that orbital lost an electron, which means it has 1 electron in its orbital, which means it'll be 1 times 0.2535 squared plus 1 times 0. Now the 0 is because the third orbital has a for that 1 electron has a 0.0 coefficient, and this would be equal to this answer for the pi charge for the first excited state. Okay. Problem 4. So problem 4 is asking you to calculate. I should really start with. So I'm going to copy the question. Problem 5. Okay. So before I do problem 5, I want to talk about row vibrational transitions. So row vibrational transitions follow a selection rule in which J can increase or decrease a quantum number. So in this case, J can only increase by 1 quantum number. So I should have wrote this down, but selection rule for J is either positive or -1. So it can either increase or decrease the quantum number. When it increases the quantum number in a row vibrational how do you mention it? A spectrometer, a spec graph, pretty much. It's called the R branch, which is usually on the right side, and then for a P branch that loses a quantum number, which would be on the left side. And I'll show you guys a picture in a second. So these spectral lines are relate, like if you relate to the energy of the transition, I mean energy between the 2 transitions. So basically it's the difference between the row vibrational transition. And when we include V of R, V of J is in regards to the initial J, and we can have 2 different V of R's. two different V's. So V for the R branch and V for the P branch. So like I said before, it's difference between so the final transition and initial transition. And during the transition, V for fundamental means that V increases one quantum number. And for overtones, it means that it increases by two quantum numbers. So when we go to, again, okay, on the spec, and I just showed you a spectrometer on here, which is for this question, but I want to go more in depth with this. Oh yeah, first overtone here. So basically, what we need to do for this question is, did I paste it? Okay. So for infrared of for helium, hydrogen chloride is very dilute gas phase has been recorded in the first overtone. So for this, it's for this transition. It's asking the first 3, 4, and 5th lines in the R branch of the spectrometer appear at these numbers, and the first, second, third in the P branch will appear with these numbers. It's asking to determine the rotational constant B of 0, B2, and of gas. So basically, for the R branch, we know this is true, and for the P branch, we know this is true, and J is the initial. Okay, so on the spectrometer, this is what it shows. So for a P branch, we have, this is for the P branch. P branch is on the left and R branch is on the right. And this would show for V of R is equal to 1 and V is equal to 2 and so on. And this is V is equal to 0 and V is equal to 1. Now, I also went in depth. You can like draw the spec out and do it that way to figure out what V of R and V of 0 are. But what I did is I pretty much just use logic pretty much, like for, so like for the nth line, so they say mention the line number, the nth line of R is equal to whatever line they mention minus 1. So in this case, they showed that I pretty much just drew this. So like Remy wrote this. So for the first line for the R branch, it relates to V of R of 0, which is equal to this equation. This answer. And for the third line, it's equal to V of R for that J value is equal to 2, and it's related to this. So knowing these facts, what we can do is plug in these here. So we need J values that are equal to each other. So to find what V of 2 is and plug in. So we know that V of R and V of P of 2 are both have the same J value. So we subtract these by each other and then we solve for it. Now, what J we use is just J of 2 because that's the initial condition we did. And from that, we solve B of 2 is equal to this value. And the next part is asking you to solve for B of 0. So we need a J that's two higher than this one. So then we have J of V of R, which is V of R of 0. And then we need something that's two higher for that V of P. So then we have V of P 2, which we have here. And then we found that B of 0 is equal to this from solving it. And in the previous J value we use is 0 because of this here. It's dependent on the J value of V of R. Okay, so from here, part B is asking you to determine the rotational constant. Determine the rotational constant B of E for the row vibrational rotation coupling constant A of E of hydrogen chloride. So for that part, B of V corresponds to to V. So basically, this is a first overtone. So we can use these two equations here. We can use this equation. And so we try to find B of 0 and B of 2. So we just plug in B of 0 to find B of 0, and we plug in B of 2 to find B of 2. Now, this is great, but we have two constants, but we also have two equations here. And I mean, we need to find these values here, but we have B of 0 and we have B of 2, which is shown here. Right, so that means we have to find what we can plug in what we got, and we can subtract them and then just solve them like linear set of equations. So basically what I did is I basically subtracted it by multiplying by -1, crossing these out, and then we're left off with these two. And after solving, we get this value here. Now, after solving for that, we can plug in this into the original equation, and we get B of E is equal to this. And that should be centimeters to the -1. But yeah, and part C is a little, I don't want to go too much in depth with this. It looks like a recitation question for some reason. Like he just wants you to plug in, like I can usually walk through with this. Pretty much you know what B of E is equal to, so now you solve for it, what R E is, and then you find that this is equal to this. So then you solve for the reduced mass, and you solve it, and you can use AMU, and you can convert it back into grams by just multiplying by this. And then what he also did, since we have centimeters to -1, we can use I believe CGS units. So then we use ergs and we use seconds, because H bar is in terms of ergs and seconds squared. I mean ergs and seconds, but in this squared, it's erg second squared, second squared. And what he did too was 2 times the reduced mass, and then BE, and lastly HC, because we are using wave numbers, which is in terms of which is kind of like wavelength, so we have to divide by HC, and then we get RE is equal to this answer. Like, I'm sorry I didn't go too much in depth with that, but it's I would say to follow the question if you understand it. All right, does anyone have any questions with this question in specific at all? Okay, so what I did for the next part is I went over one topic that you guys learned. So basically Boltzmann distribution. You guys learned this, right? Boltzmann distribution. Yes, no, maybe. So, wait. 1 second. All right. I'm assuming you guys learned it, so let me just go over it. So Boltzmann distribution has to do with finding the distribution, like with energy states. So we can basically solve for it based on the distribution of energy states, and we can use these equations to solve for it here. So beta is equal to this quantity over this temperature they give you, and Q of T is pretty much the sum of that distribution. So pretty much that, and G is related to the number of degenerate states you have. And if they're talking about relative to the ground state, you're gonna have a difference in energy from the ground state instead. And average energy is also related to this equation, which is that Boltzmann distribution you solved multiplied by the energy of that. energy of that state. So let me go in depth with like one example. So let's say consider a molecule with a two systems but a non-degenerate ground state labeled 0 and a threefold level labeled 1 with energy expressed in wave numbers. So I drew this, so it's threefold degeneracy. There's three states at the same energy level, and there's a non-degenerate state, which means it's only one state. It's asking you what is the probability, what's the portion n1 over n of the molecules in the higher level, t equals 200. So we can just plug it in. So g of I over times that e to this, because it's relative to the ground state, we have to use a difference in energy from the ground state. And we know it's g of 1 and then this here. So then we just plug in. So we solve this separately in the exponent. And we found that this is that constant that we talked about over the temperature, which is given to us, 200 Kelvin, times the energy relative to the ground state, which is 50 centimeters negative 1, which is equal to this value. And we put that in exponent. Now, and this is also the sum of all the states. And there's, okay. So next part is just to plug in. And g of 0 is, because there's only one state, we're going to have it equal to 1 because the non-degenerate state for that. And since it's relative to the ground state, so that energy relative to the ground state is just 0. So the difference between energy from the ground state is just 0. And then this state here, we just plug in the exponent, which are the same. And then and then after solving for it, we get this answer for our distribution. It's pretty much kind of relates to the probability of finding that a particle with that energy level. Now, does anyone have any questions about this part? Okay, so next part is to find the average energy. So it's the sum of the distribution here. So pretty much distribution we solve. Now, and the difference between the ground state. The difference between the ground states. So basically, we found that P of 0 and the difference between the ground state, like the relative to the ground state is 0, so we don't need this. We solve for this part here in the first question. So then this is going to be equal to this times the energy relative to the ground state, and we're going to get this answer for our average energy. And part C is pretty much doing the same thing, but you're doing it for the ground state. And since the ground state times 0, and you're gonna find this is equal to this. And I want to go in depth with it for part D. We're going T to infinity, so it's asking you to do what is the proportion at higher temperature where T goes to infinity. Like I mentioned before, the normalization part in exam 1, when you go into infinity for an exponent, and since this is the T is on the bottom, this T is going to infinity, and 1 over infinity is approximately equal to 0. So then you're going to have each exponent is going to go to 0. It's going to have e to the 0, and that will just equal to g of 1 plus g of 0, and that's just 3 plus 1, 3, and then 3 times 1 and 0.75. So what this really means, at higher temperatures, distribution will go to the higher energy state, which makes sense because if you're at a higher energy, you'll have to go to a higher energy state. Now, that is my full. Oh, you have a question? No. Does anyone have any questions with this part or any part of what I? Yeah, what's up?
Sorry. So for your part C in this question,
Yes.
on the sample answer, n0 over n would be 1.
It'd be 1.
Yeah.
For part C, you said?
Yeah, for part C.
Why would it be? Oh, why do you say it's 1?
Because I don't know like why you're doing the QT, but on the simple answer it's just G0 over G0 plus G1 times e to the negative delta V over T.
Delta V over T. Huh. Oh, so I'm not sure what you're talking about, but what I'll just explain what I did pretty much. It's Q of T is just equal to that sum here. I didn't list it off because so basically when I got that sum here, I got it equal to this underneath. And so that's pretty much what that is. So it's pretty much the sum down here, which is just this.
Yeah, but for part C, the temperature approaches 0, so I guess that's where.
Oh, you say it's approaches 0? Oh, I see what you mean. Okay.
Oh yeah, that's.
Yeah. Okay. Yeah. Okay. So this is from my old exam, and I assumed it was the same temperature, and I think that's why I got the 3 points off. But okay. So yeah, I see what you mean. Because it's at 0. Yeah. And because of that, you're gonna have
1/1 at the end.
1/1, which shows. Okay. Yeah. Thanks for that. And yeah, this makes sense because if you're at a lower temperature, you're gonna be at closer to the ground state. And I mean, you're gonna be exactly at the ground state. So you're gonna only find a particle at the lowest state, which is the ground state. Okay, thank you for that. Now I know why I got those points off for my final. Okay. So does anyone else have any other questions with this? Any at all? Like it can be any part or any questions you want to go over. Okay, so if no one has any questions, then I guess we can end the review. Let's stop broadcasting.
You guys be here tomorrow?
I am not. How about you, James?
Or Thursday, I think.
I don't know because I think office hours ended. It depends on James's schedule. Wait, is James you here? Here, let me hold up. Let me call him. I will get the answer. If he has office hours, I might show up.
What's up?
He wants to know if you have office hours.
I am not holding office hours anymore because I have to study.
Okay.
I mean, unless enough people want to do it, then yeah, sure. I'll hold one like either tomorrow or Thursday.
Yes, sir. Sounds good. So yeah, enough people show up. Or you can just shoot me an email on my SBU if you have any quick questions. Sound fair?
Can you go over problem 2 on the final exam?
Problem 2, is that last year's final exam?
Yeah.
Okay, yeah. I actually have a solution for that. So, okay, now I know where I lost those 3 points, but okay. Wait, is this the final exam actually? Yeah. Problem 2. Okay. What infrared spectrometer is the study of a diatomic molecule XY given in the following information? Okay, at what frequency would you have the lowest line? Okay. At what frequency expressed in wave numbers would you find the lowest energy line of the R branch? Here in iron. Okay, I'm trying to put it in my mind here. Okay, so the lowest line in the R branch would be when J is equal to 0, and that means the transition 0 to 1, because if you really think about it, the R branch goes like this. Oh wait, yeah, there we go. Spectrometry goes like this. This is a bad drawing, but this is going to be V equals 0. And since it's mostly on the left, this is the left corresponds to less energy. And so that means that, sorry, I'm running my thoughts. The more left you go, the lower transitional energy. So it's V equals 0, you have to find. So now you found your J value. Now, they've given you what BE is equal to, what AE is equal to, and they want you to find, and they want you to plug this in. They want you to find B1 using these quantities that are given to you. So basically, alpha and VE. So now you have B1. So basically your overall goal is to use this equation. And to use this equation, they have to find they give you W, you have to find what B1 is equal to and what B0 is equal to. So then for the next part, you have to do the same thing, but except you're gonna have to find, you have to plug in V is equal to 0. And up here, you plug in V is equal to 1. So B1 and B0 relate to V is equal to 1 and V is equal to 0. Now, do you have any questions so far about this?
I'm good.
You good? Okay. So after you plug in those values and you find your B1 and B0, you just plug it into this equation and then just solve what the frequency is. Okay. Does that make sense?
Yeah, that's great.
Okay.
Okay. Still, I have one more question on the problem 5.
Problem 5 to say exam.
Yeah, on this. Yeah.
Okay. So
So,
as I consider a state to its electron molecules AB is wave functions. Okay. Okay, what was the value of the interval so that the complete spatial and spin wave function is normalized? So they basically wanted you to find a normalization. Yeah. They want you to find like the normalization, basically the normalization constant. And my thoughts. All right. So okay, yep. All right. So then we have Okay, that. And then we're here. So much. Okay, so I believe what I did for this was so basically I tried to normalize it itself, and then the normalization consistent equal to 1. So then I used Brown-O'Kent notations over here. And then what I did was, since the spin part are normalized, I don't know what this is. I solve for this here. And what I do is I find this is equal to 2. And then basically finding that normalization here. And then I equal this to 1/2. So basically I saw what this the spin part integral is, and then I equal it to the other side. So I basically have to equal it to 1 overall, right? So then I put everything on the other side, and I find that this has to be equal to 1/2. Does that make sense?
Yeah, that is.
Okay.
Thank you.
Yeah, no problem. You have any other questions?
I'm good right now. Thank you.
All right, so no problem. You can email me or James if you have any questions. Okay. Let's see what else. Anybody else have any questions at all?
Hi. When is this video gonna be up? The recording gonna be posted? Because I'm probably gonna go through this again.
Okay, it will be posted when James posts it. Which
As soon as it's processed and YouTube is like, yeah, we can do this.
Okay, cool.
Since it's less time than the last 2 reviews, it's gonna probably be less time than before. I'm not gonna quote it. Like, I'm not gonna like make false promises, but it probably is. But yeah. Anyone else got any questions? None at all. All right. I saw you guys' exams. Pretty tough stuff, I have to say. Like our last year exams were like not that difficult. I think he does it hard because it's in person, but still, you know. But you guys are like at the finish line, so. And if you guys worried about your grade or anything, he does curve it. If you guys are getting like 70s, you pretty much got an A. I know that for sure. And yeah. Okay. No one has any questions, you're free to go. The recording will be posted by James. They can post in the group chat as soon as it's done.
Okay, I'm gonna stop recording.